So it's my great pleasure to introduce Rafi Stern. I've actually known Rafi since he was a senior in college. In 2013, we met. He got this pretty cool fellowship to travel around the country and visit grad schools. So I got the chance to show him around Berkeley and get a lesson on how actually recycling factories work, of all things. So one of his many interests outside of his research, you can ask him after the talk. So Rafi is currently assistant professor in the Department of Civil, Environmental, and Geoengineering at the University of Minnesota. His research interests are in traffic control and estimation, with a particular focus on connected and autonomous vehicles. And he's worked on a lot of cool experiments with connected and autonomous vehicles, and hopefully he'll talk about some of that today. So Rafi, over to you. Looking forward to talk.
Yeah, thanks a lot, Samitha, for the introduction, and thanks for the opportunity to present here at Cornell. Despite being here virtually, I'm very excited to be at Cornell. I've wanted to go visit and see the university for a long time, so I think this is sort of like a second best thing. A few things. There's a Calc 1 lecture happening in the room next door, and so hopefully the bandwidth holds up, and hopefully I don't get too distracted by hearing about volumes or rotation. But if let's hope that all works out. If I seem distracted at times, though, that might be what it is. What I'm going to talk about today is, like Samitha alluded to, some experimental work and sort of trying to make mathematical sense of some experimental findings. As a civil engineer, I really like to get my hands dirty, so I like to play with both the theory and some of the experiments. So hopefully I can give you a little flavor of that. The work I'm going to talk about today is joint work with my collaborators, both sort of current and former collaborators, including my grad student, Ming Feng, who's realistically done the bulk of the heavy lifting on a lot of this stuff. So if you're impressed, talk to him. If not, talk to me. So what I'm interested in is automated vehicles. And obviously there's a lot of ways that automated or autonomous vehicles have the potential to change really fundamentally the way we think about transportation. And so as we look at there's a lot of different ways in which we can ask the question of how are autonomous vehicles going to change things. One of them is what's going to happen to, for example, vehicle miles traveled, VMT. And there's sort of two different potential outcomes. There's one where we think about these pooled shuttles, right? So a whole bunch of people get in. I used to, say I go to the airport. That doesn't happen anymore. But people at some point, used to go places, and they, if there's a lot of people say headed from campus to the airport, it makes a lot of sense for them to share that ride if that's happening both in terms of spatially and in terms of the same time. So you can imagine you could pool a lot of trips. Pooled trips means fewer individual vehicles driving, means fewer vehicle miles traveled. But if you look at the autonomous vehicle not as a pooled shuttle, but you look at it as your personal chauffeur, all of a sudden you might think that driving becomes a whole lot more desirable, because instead of having to do the driving task myself, I've got my chauffeur who picks me up and drops me off, and then maybe picks up lunch for me while I'm at work. And so you can imagine a scenario where vehicle miles traveled really, really increases. The other aspect that you can look at is, well, what happens to land use? Actually, David Schmoys and I were just having a conversation about exactly this. There's the one scenario is you don't need that much parking anymore. And so you have all this extra space. You could use this extra space for higher density housing, extra parks. You could use dedicated lanes for buses to make the city traffic run more efficiently. So you can imagine cities could become a lot denser, maybe a lot more efficient from that perspective. But the other sort of example is, well, think back to the chauffeur. The chauffeur can drive you to your place if it's a 2-hour commute. That might not be so bad anymore, because you can sleep, watch Netflix, eat breakfast, do work, all in the comfort of your automated car that's driving you there. Another aspect that you can look at is safety. And the cool thing is, while the other sort of the vehicle miles traveled and the land use things, they come in really at higher levels of automation, sort of fully automated vehicles where you don't need a driver anymore. Safety has benefits right now at much lower levels of automation. We start to see benefits from safety in terms of things like braking assist, lane caping assist, things like that. The question that I'm really interested in is, how will increased vehicle autonomy influence the traffic flow? How will it change the dynamics of how the traffic behaves? And how do we properly model that to understand and maybe try to sort of see how things will change in the future? Specifically, what I'm interested in is something called phantom traffic jams. We see them at the top in the wild, so to speak, on actual roads. These are traffic jams that arise not because of some sort of fixed bottleneck in the road, such as construction, police, or a reduction in lanes. But these are bottlenecks that arise because of how humans drive, just human driving behavior alone. And so at the top, we see this is a road, I think, somewhere in North Florida. And you see there's this traffic wave that's going to start here and sort of propagate upstream. And I'm sure you've probably experienced this as well. There's a slowdown, you come to a stop, you keep driving, but there was never any sort of real reason why that traffic jam should have occurred. And it turns out for a long time in the traffic engineering community, this was a big debate. Are these phenomena that are result of human driving, or is there always some infrastructure trigger that's involved? So in 2008, I really like this narrative because sort of like the engineers were arguing over it, and some physicists said, well, let's just do an experiment. Let's see what happens. So they came up with this really clever idea. You have 22 vehicles on a circular track. All of the vehicles start with the same speed and same spacing. You don't have any sort of, infrastructure related bottlenecks that could cause a traffic jam. And sure enough, relatively quickly, that smooth flow turns into this stop and go wave. And this experiment, as part of my PhD, I basically redid this experiment 26 times in total. And every single time, here's one of the videos there, every single time you see this stop and go wave emerge. It's almost inevitable that if you have enough humans on a track, human drivers amplify the waves, and you get a standing wave, or you get a wave that propagates upstream. And so what's really going on mathematically is something called string instability. So put simply, string instability, if you imagine a platoon of vehicles at equilibrium, so they're all driving with no acceleration, i.e. same speed and some constant spacing. If you have a string of vehicles like this, and the one vehicle in the string has some disturbance, if that disturbance amplifies as it propagates from one vehicle to the next, we call that string unstable. And if that disturbance dissipates from one vehicle to next, we call that string stable, right? So string stable means that further on, and importantly, all these vehicles eventually, each vehicle individually returns to its flow. So it's, it's asymptotically stable, sure. But the question of string stability is really what happens to that perturbation as it propagates through the string of vehicles. And so it's pretty clear experimentally that human drivers are string stable. And a lot of work that I did in the past was sort of understanding, well, what happens if we swap out a small number of those human drivers with automated vehicles? Can we change the emergent properties of the flow? So you see, the fully human driven traffic does in fact yield the that string unstable flow. And it turns out that it's relatively straightforward from a control standpoint to design feedback controllers that achieve string stability on the ring by just changing the dynamics of a small number of vehicles. So basically swap out one of these vehicles on this ring here, and it turns out you can relatively easily achieve string stable driving. And so what I want to show you sort of to motivate where I'm going to go from here is work that I did as part of my PhD to show how this might look. So this is one of those experiments that I did. You have the same 22 vehicles on that ring road. All of them are human driven right now. The vehicle with the black arrow on top of it is an autonomous capable vehicle, which means that we can press a button and it can activate a pretty simple feedback controller that is able to stabilize the traffic flow. And you see, if you look at the speeds down here, you see we start with that, relatively quickly under human control, that instability starts and those traffic waves emerge. And then as soon as we start to actively stabilize the flow with the automated vehicle, we see that we can get much, much smoother driving. And so the interesting thing here is really that we're not changing the dynamics of all that much. 1 in 22 is marginally less than 5%, but changing the dynamics of only 5% of the flow completely changes the emergent properties of the flow. And so what we'll do shortly here is we'll turn off the automated controller in the experiment, and you'll see again that stop and go wave arises pretty quickly again. So now we're back to human control, and just the way human drivers behave, we're going to get that oscillatory behavior. Okay, so we can look at the data from this. And unsurprisingly, what we're looking at up here is, in traffic engineering, we call this a space-time diagram. It really just means that we plotted the position of each vehicle in space over time. And so each of those lines represents the trajectory of one vehicle. And what we see is, sure enough, pretty early on, we saw those waves emerge. As soon as we start activate the automated vehicle, again, the take-home message here is really just changing the dynamics of a small number of vehicles can substantially change the dynamics of the traffic flow. And we see very big savings in terms of fuel consumption because this unstable driving here is really the worst from a fuel consumption standpoint. This hitting the brakes, hitting the gas is really terrible from a fuel consumption standpoint. Okay, so that's what happens if you have full control over a small number of vehicles, and you can really tell that vehicle exactly how to drive. So this is sort of, in the interim, if we have fully automated vehicles, we don't need all the vehicles to be automated, but just a small number of automated vehicles. If we can have full control over how that vehicle behaves, then we can use that to, well, make a pretty big impact in how the vehicle behaves. But I want to sort of use this to motivate what I want to talk about next, which is really that not all automated vehicles are the same. The Society of Automotive Engineers defines 6 different levels of autonomy, starting from level 0, which is no automation. So the car that I drive, this is a level 0 automated vehicle, right? There's, steering, acceleration, that's me. Monitoring the environment, that's me. If something goes wrong, that's the human driver who needs to intervene. There's no robot on board. But as you go up the spectrum of autonomy to driver assist, partial automation, conditional automation, high automation, all the way up to full automation, you go from, you start to hand off more and more of the driving tasks to the automated vehicle. And so until you get to level 5, this is sort of what you may think of as an automated vehicle, but really these lower levels of autonomy are already taking over some of those driving tasks. And so, in fact, the feature that I'm most interested in is something called adaptive cruise control. It's really a level 1 automated feature. Some of you might actually have this. It's basically radar-assisted cruise control. So you use a front-mounted radar on the vehicle to see how far are you from the vehicle in front of you. And then you use that to determine how fast you can drive. So you have some set point, say, just like typical cruise control, I want to drive at 60 miles an hour, but I also want to follow at a safe distance. And so that vehicle will drive at 60 miles an hour unless there's not enough space on the road, in which case it'll slow down to avoid a collision. This is not a new feature by any means. It's been around since the early 90s. Historically, you get a premium vehicle and then you pay an extra hefty sum to get it as an add-on to a premium vehicle. And so until now, it's really not been a large part of the traffic flow. And so I don't think it's really been a large concern of how do these vehicles actually drive from when you think about longitudinal dynamics or longitudinal control. But that's starting to change. And so I've already told you that just changing 5% of the traffic flow dramatically changes the emergent properties of the entire flow. And we're at the point now where if you look at the 20 best-selling cars last year, 16 of them were were sort of level 1 automated vehicles, or at least available with level 1 automation features such as adaptive cruise control. So this tells us that we're at a point now where relatively soon, a large number of vehicles are going to drive substantially differently. And in the one case, when you had full control, we could design them to be beneficial to the flow. But the question is, how are these vehicles designed and will they actually be beneficial to the traffic flow? And that's really the question that I want to address. So the question I want to look at is how do we accurately model these low-level automated vehicles? And then how do we analyze those vehicles or that vehicle behavior to understand what it's going to mean for things like traffic string stability? So that's really what I want to do next. Okay, so how do we go about modeling the automated vehicles? So to look at ACC or partially automated vehicle stability, I want to have some sort of modeling framework. What I'm going to use is an ordinary differential equation to model the dynamics of a vehicle. This is quite common in traffic flow theory, and it's an idea that really dates back, I think, to the 1950s. And it's the idea that my acceleration is a function of my surroundings. I accelerate with a speed that depends on how fast, what the traffic conditions are around me. Specifically, the acceleration of a specific vehicle is a function, generally assumed to be a function of how much space do I have in front of me? Is the car in front of me really close or not? The relative speed with respect to the vehicle in front of me, i.e. are they catching up or slowing down? Or am I catching up to them, or are they sort of running away from me? and the speed of the vehicle itself. And so you can imagine sort of a relatively simple ODE can be used to describe the dynamics of a following vehicle as a function of the leader-follower, the state of the leader-follower state. And when we model this, we generally have these what we call rational driving constraints, which are basically requirements on the behavior of the ODE that we want that sort of makes sense from a driving perspective. And so I guess the idea here is if we're modeling traffic flow, we need it to be realistic traffic flow. And so these are, I think, quite intuitive. If you look at sort of the partial derivative with respect to your spacing should be positive, i.e. as your spacing increases, you tend to drive faster, i.e. you don't hit the brakes when you have more space on the road. As the lead vehicle speeds up, so your partial derivative with respect to the relative speed should be positive, i.e. as the lead vehicle, we're defining our relative speed as speed of the lead vehicle minus speed of the following vehicle. So as the lead vehicle races away, you don't hit the brakes, or possibly more importantly, as you catch up to the lead vehicle, you don't accelerate. I think that one's probably pretty natural. And finally, at higher speeds, you generally tend to accelerate less. So you don't, you accelerate a lot at lower speeds, and then you have some sort of steady state behavior that you want to tend toward, and then you don't accelerate as much. So with these three rational driving constraints in place, what we want to do is we want to look at how, if you couple multiple of these ODEs, how will first of all, we need to define the equilibrium, and then how do disturbances propagate through that, that system of coupled ODEs. So remember, so just keep in mind the notion of string stability. It's how does that disturbance propagate through the traffic flow? We're going to define our equilibrium flow as being the case when we have all the vehicles driving with no acceleration and the same speed, and thus the same, so same speed, i.e. no relative speed, and no acceleration, and some constant spacing, equilibrium spacing. So there's a family of equilibria that live along that spacing for the same, spacing, the spacing and the speed determine the equilibrium, but for the speed, there's one, for an equilibrium speed, there's a unique equilibrium spacing. If we assume a homogeneous traffic flow where all the vehicles use the same ODE. And so then we can introduce some small disturbance to that equilibrium spacing. And the question of string stability is, how does that small disturbance propagate through that flow? So in order to do this, we're going to look at a linear stability analysis around that equilibrium, so in the neighborhood of that equilibrium, and we're going to insert that small disturbance into the leader, and then see how that propagates to the follower. We're going to do this in the frequency domain. So we're going to basically look at a forcing function on the right-hand side and find the transfer function of that disturbance. And then we look at the Bode plot for this transfer function, and it turns out that if we assume the rational driving constraints apply, there's really only one of two possible shapes for that Bode plot. And so we can look at the curvature of the Bode plot to identify, it's kind of a nice trick that allows us to very easily identify whether or not a particular car following model is string stable or not. We can basically just look at the curvature of that Bode plot. So if we look at the Taylor expansion of the Bode plot at 0, that's going to tell us curvature, i.e. is it always concave down? Are we always string stable? Or sorry, is it always negative? So are we always string stable, or do we go up first before we go down? So at the end of the day, we can come up with this relatively straightforward criterion for close to that equilibrium. We just need to compute this lambda2 value, which depends entirely on the partial derivatives of the particular ODE that we're looking at. And if that lambda2 is negative, that means that we're always going to be string stable. Whereas if that lambda2 is positive, there's going to be some range of disturbance frequencies for which we'll amplify those disturbances through the traffic flow. I want to pause here just to make sure that we're clear so far. Okay, great. So the goal of, so with this sort of simple mathematical concept in mind, the goal now is to find an ODE that matches the behavior of these commercially available automated vehicles, collect data on those automated vehicles, and then calibrate those ODEs And then we can easily analyze those ODEs to say whether or not we think those vehicles are string stable or string unstable. And that's sort of the approach that I want to take from here. So I'm going to sort of switch over to the more experimental part of this, which is basically going out and observing ACC vehicle car following behavior. And the experimental setup that I want to use here is actually really straightforward. You go to Enterprise, you get a commercially available adaptive cruise control vehicle. You have a lead vehicle that follows some predetermined speed profile. Then you look at the following vehicle is following with ACC on, get GPS on both, and you basically record how the follower responds to the leader, right? So in this is often called, like system identification. We're basically just trying to identify, we have an input signal in terms of speed and spacing. In terms of speed and speed and spacing, what's the output signal going to look like? And that's really what we want to do, is identify what gives us that output signal that we observe in the following vehicle. So in terms of how I want to model these vehicles, if you look at adaptive cruise control literature, there's a whole bunch of different proposed controllers. The challenge is I'm really interested in this not from the vehicle control perspective, but sort of zoom out a few levels. I want to look at this from the traffic flow perspective. So I want a traffic flow model that's compatible with with how traffic flow behaves, not necessarily a vehicle level model that tells me how the dynamics of the sort of what we're telling the engine, but really what are we seeing in the terms of the vehicle's behavior. And so there's a whole lot of nonlinearity that happens between what you tell the engine and then how that translates to the drivetrain and then how that actually translates to sort of rubber moving on the pavement. That I'm not actually that focused on that. What I'm focused on is I care, how does the vehicle behave at the level of traffic flow? Does it accelerate, slow down? And then how does that play out? Because what I really care about is how does that play out in the overall traffic flow? Imagine thousands of these driving on the road. So the ODE that I'm going to use for this is based on the idea that, well, most ACCs use something called a constant time gap or a constant headway. So basically, if you think back to driver's ed, you might have learned something called the 3-second rule. The 3-second rule says you should always be 3 seconds behind the vehicle in front of you. So if you drive twice as fast, you leave more space behind, right? And so the idea with this is basically we've got the actual spacing minus, this is sort of our desired spacing, which is based on a constant time gap plus some safety buffer. And then we have, so this is, you can think of this as sort of an error between how far behind the vehicle we want to be and how far the vehicle we actually are. We got a gain on that error. And then we've got a relative speed and we've got a gain on our relative speed, which is going to try to get us to match the speed of the vehicle in front of us. So this model is quite simple. It has 4 parameters that we can tune. So if we have experimental data, we can do some optimization to model simulation-based optimization to identify what parameters K1, K2, tau, and eta we want to find in order to get behavior that matches the actual sort of the traffic level, I'll call it behavior, of the following vehicle.
Excuse me.
Rafi, I think Alex had a question. Sorry.
Yeah.
Go ahead.
I apologize for interrupting. I just really want to make sure that I understand the definition of string stability. The lambda 2, which you are computing, this is evaluated at the parameters v, delta v, and delta x. So could you have something string stable for one value of delta x and string unstable for a different value of delta x?
No, I don't think so. So a delta x is a particular spacing, and keep in mind string stability is only defined at the equilibrium. So for a particular value of delta x, we've got a particular speed. And are you saying could you be string stable at certain? Yeah, okay, I see what you're saying. It depends on the model you use. For this model, I believe the answer is no. But you can get models where so if you use, there's another very popular traffic flow model called the intelligent driver model. This model is quite nice, but the problem is if you look at it in let me go back a few slides. If you look at it in the lambda 2 space, you are now dependent on your speed. And so in that case, you do have the case where for some equilibria flows, you're string stable, and for some equilibria flows, you're string unstable. But for this model, I'm fairly certain that you for any delta x, you're either string stable or string unstable.
Got it. Thank you very much.
Yeah, no, thank you. Okay, so with that in place, then we looked at 7 different vehicles. It was what could we get our hands on, basically. So this ranged from a small compact sedan all the way up to a very large SUV. And we're going to put basically every single one of these vehicles through the same protocol. So there's a whole bunch of different tests we did. The lead vehicle drives, we want to get oscillatory behavior. We want to see that, the change. We want to see it basically try to approach an equilibrium. We want to see shocks, or not shocks, but we want to see disturbances. So we look at oscillatory driving. This is the lead vehicle data collected via GPS. And then you see the following vehicle data. We did this, for several different speeds for all 7 vehicles. So then basically the total, the whole pipeline then looks something like this. So we start with our 2 vehicle experiments. This produces our leader follower trajectory data. We take that, put that into a simulation-based optimization where we try to find the parameter values that best match our simulation. And then for a particular vehicle, we look at we get vehicle A, for example, at the minimum setting. So these ACC vehicles have different following settings. You can follow the 2-second rule, or you can follow the 1-second rule effectively. And so you can drive either closer or further away. And we looked at it at both the furthest setting and the closest setting. So at the closest setting, this vehicle, it turns out that for this model, we really only need K1, K2, and tau to determine string stability. And so we get values for K1, K2, tau. We get a mean absolute error in terms of seconds. So we're trying to minimize our headway error. And we can then use this to compute our lambda 2. So you can see that this particular vehicle at the closest setting is in fact string unstable. So we can then sort of look in simulation. Well, what does this actually look like? In blue, we have our simulated speed, spacing, headway. And in red, we have the real. And you can see that, for this model, very simple ODE actually captures the dynamics of that vehicle surprisingly well when you look at sort of the traffic level behavior. We actually get surprisingly good fit, both in speed, spacing, and headway. Okay, so then we do this for vehicle A at the maximum setting, vehicle B, vehicle C, vehicle D, vehicle E, vehicle F, and vehicle G. And I want to sort of call 2 things to your attention. The first one is if we look at the error. In general, so this is a headway error. So if we're following the 3-second rule or the 2-second rule, in this case, these vehicles you can see follow something like the 1.5-second rule or the 2.5 roughly second rule. Our estimates are on average off by something like a 1/10 to a 20th of a second. So that's actually pretty low error. And I'm going to be honest, I was surprised that this very simple ODE is able to capture really a good amount of that data, or of that driving behavior that we see in the data. The second piece that I want to point out is if you look at the lambda 2s. And so this means that every single one of the vehicles that we looked at is in fact string unstable, right? So all of the commercially available vehicles that we looked at, that we were able to get our hands on, were in fact string unstable, meaning that they amplify disturbances. Now, I started this talk by saying, yeah, go ahead.
So in your simulation-based optimization, do you know how close you are to actually optimal? Do you have any sort of certificate of optimality? And if you are suboptimal, could that actually affect your conclusion about stability?
Okay, so let me answer that in 2 parts. The first part is I don't know. And we just used a pretty simple solver in MATLAB, I want to say. So I don't know, but I mean we did a whole, you do a whole bunch of different trials, and you look at what's your best. It's possible that we are not at optimal. I will say though that I've done some sensitivity analysis on this, and it turns out that your string stability result doesn't really change, even with other solutions. So I looked at how much can I perturb the optimal and still be string stable, and the answer is you can perturb it quite a bit and still be string stable. And if you constrain it to say, I need my lambda 2, like I need to be string stable or I need to be string unstable, what you end up getting is, if you constrain it that you only want to consider solutions that are string stable, then you get, I mean, if you imagine in your space, you have sort of a boundary where you are string stable, you transition between string stable and string unstable values. If you constrain it to be string stable, then you always end up with points that are right on that boundary. And so I'm pretty sure that that doesn't influence the, so I'm not certain that these are the best, that these are necessarily the best values, but I'm pretty certain about the string stability conclusion from that optimization. Now for the second piece, and this is going to get into what I want to talk about here in a minute, is, okay, but how does that, I mean, I started talking about saying human drivers are string unstable, right? And now I've shown you that adaptive cruise control vehicles, commercial ones, are also string unstable. And I think the question is, well, what is that going to mean for traffic flow? And for that, Carlos, there's the quality of the models does matter, right? So even if the string stability conclusion may not change, the behavior that you get in the models does matter. And so I think that's something that I'm still working on, trying to figure out what's the best, like what are actually the best parameters, and how do and I think you could definitely expand to a larger search space in terms of other functions as well, right? I'm only looking at functions of the form that I presented, but you could certainly look at a larger set of functions to see if you can find a better fit. Does that answer your question, Carlos? Okay, awesome. So, okay, so then the next question is sort of, what does this mean for traffic flow, right? Like I said, we started by saying human drivers are unstable. We've concluded that ACC vehicles are unstable. Does that mean traffic is going to get worse or better? Because we know that changing the dynamics of vehicles does change the traffic flow. And so what we're doing for this is I want to just basically run through a simulation where I can couple a whole bunch of these ODEs on a large network or medium-sized network. So, a couple kilometers of roadway, and look at a merge and say, what happens on this merge if you have 10% of vehicles look like this, or 20% of vehicles look like this, in comparison to sort of a baseline human-driven traffic flow. And for this, we're going to use, pretty standard calibrated models for human drivers. That has been, calibration of human driver models has been done for a long time. And we're going to sort of mix those with some of the drivers of the type that we have, as well as some models for what automated vehicles, sort of optimistic models of what automated vehicles might behave like from a traffic flow perspective in the future, and sort of be able to compare those. Now, in order to understand the results that we're going to get here, I want to take a quick detour into a little bit of traffic flow theory, go back about 95 years to, if I'm doing the math right, to 85 years. Thank you. Yes, 30, yes, okay. Yes. So to the early 1930s, this guy, Bruce Greenshields, was a professor at Ohio State University. And he had this theory that said that basically the speed that you drive on the road ought to depend on how many people are on the road. And we had an interesting conversation at lunch today with the students about how did he ever even think about that, right? I mean, like, you have to imagine this is in a time when there really weren't that many vehicles on the road. So he went out and he wanted to collect some data. And so he went out to the Ohio Turnpike and he collected a bunch of data with cameras where he identified, when a vehicle passed one location and another location. He looked at the data. He mostly had a bunch of data here so if you imagine this is the density and this is the speed that they're traveling at. He had a lot of data here at very low densities, perhaps unsurprising, and high speeds. And if you look very closely, you'll see that what he considers high speeds is about 40 miles per hour. So things have changed a little bit, but he has some data over here, and then he somehow got one data point over there that was at very high density and very low speed. And so he did what I think a lot of us engineers do, is that that looks like a straight line, let's draw a line through it, right? But if you assume this flow density relationship, right, or sorry, this speed density relationship right here, then you can sort of take it to the next step. And so basically this is a linear speed density relationship. You can take it to the next step and get what we call, in traffic engineering, we call a fundamental diagram, but it's really nothing other than a flux function or a flow density relationship. And what this, if you assume this linear speed density relationship, you get a parabolic flow density relationship where you start with no vehicles on the road, and so there's no flow. And as you increase the density, so increase the number of vehicles on the road, they're going, they're zooming along because there's nobody really to block them. And so our flow increases up until some critical density, at which point additional vehicles on the road actually hamper the other vehicles from driving so much that our flow decreases again until we go all the way to the case where you imagine a parking lot where all the vehicles are bumper to bumper, no one can move. You have a lot of vehicles, but there's no flow. Okay, so with this in mind, we can basically run that simulation on that network and then look at, we can look at a couple different detectors. What does that flow density relationship look like from simulated data under, different ACC vehicle adoption rates? And so what we get is not quite as nice, let's say, as the nice, clean flow density relationship. But this is pretty common when you look at data, is that you see a very nice, we call this the free flow region, and this the congested region, a very nice smooth free flow region, and then there's sort of a scatter of data points in the congested region. And if you look at the entirely human-driven traffic, you see a maximum capacity somewhere around 1,800 vehicles per hour per lane. If you're a traffic engineer, you say that checks out, that makes sense. But as we increase the number of automated vehicles or adaptive cruise control vehicles, we see that capacity, that maximum flow starts to go down, all the way down to an almost 40% reduction for this one particular type of vehicle in terms of capacity. And so what that looks like across the fleet of vehicles that we looked at is, if you look at that theoretical vehicle that is designed to be good, turns out that ACC vehicle at high market penetration rates is able to increase the traffic flow. But all the other commercially available vehicles actually sort of spell a possible decrease in traffic capacity in the near future. So not quite as extreme as one vehicle really trying its best to do really good, but you do certainly see maybe a 35% reduction in potential capacity if we start to see more and more of these adaptive cruise control vehicles. Okay, so now that's upstream. It turns out, though, if you're past the bottleneck, you're past the bottleneck, so you're in free flow conditions. And because these automated vehicles can drive with a tighter capacity, you can get more vehicles on the road. But again, you're downstream from a bottleneck, and so that bottleneck ends up being the dominating factor. Okay, so I want to pause here and sort of pivot a little bit from the microscopic world and modeling, individual vehicles, and pivot to what happens from a sort of observing the traffic state, and sort of not think of automated vehicles as influencing the traffic flow, but think of automated vehicles as observing the traffic flow. So if you look at an automated vehicle, this is a Waymo car, it's got a whole bunch of sensors on it. In fact, if you look at sort of the cost of one of these things, the most expensive thing by far is the sensors. And we've already seen how when we looked at the transition from sort of just a small, looking at collecting data from the traffic flow, just a small number of locations in the flow, to really just a small number of vehicles in the flow giving you, continuous GPS traces, we saw a huge improvement in terms of traffic state estimation. And my question is, what additional things can we observe in the traffic flow if we have automated vehicles? And so one of the things that we can observe in the traffic flow is we can locally look at the density. And this is something that when you look at GPS traces, you actually have no idea of what the traffic density is locally. But all these models rely on density. And so if we could locally look how far are the vehicles behind me, how far, what's locally using radar and cameras, we could get point estimates in the flow, Lagrangian estimates of the density in the flow. And so the question that I have sort of is, how can we use automated vehicles to estimate, maybe a sparse number of automated vehicles to estimate what that traffic flow actually looks like, sort of from the perspective of trying to reconstruct the traffic flow. And so for this, I want to switch from that ODE way of thinking of things as individual vehicles to the macroscopic level, where we look at a partial differential equation. The one that traffic flow theorists like to use is something called the Lighthill-Witham-Richards, or LWR-PDE. It's inspired by fluid mechanics. It's just a conservation of mass, effectively. And it tells us how density evolves on the roadway. We're going to use that same fundamental diagram as part of as our flux function to solve to solve this ODE and to be able to identify how that traffic state evolves based on that fundamental diagram. And so the idea is, what I want to do is I want to model the bulk traffic flow, the human drivers, as an ODE, as a PDE, using the LWR-PDE, and then model a couple of vehicles that drive differently in that PDE using ODEs. Now, those ODEs have to obviously drive according to the solution of the PDE locally, i.e. they can't drive faster if there's very high density and all the vehicles are at a standstill. Those ODEs can't drive faster than the traffic flow locally. And I want to use that then to basically record densities along the flow, and then be able to determine what's the density between these automated vehicles based on what each automated vehicle has seen. Okay, so the whole system looks something like this. We have a weakly coupled PDE ODE system, i.e. we're using a PDE to model the bulk traffic flow of human drivers. We're using an ODE to model a small number of automated vehicles that drive within that human driver flow. However, note that it's weakly coupled, i.e. the solution of the PDE influences the ODE, but the ODE is not going to influence the PDE. So we're not going to change the flux function locally based on the solution of the ODE. And the goal is to find the time at which we can actually, if we have two vehicles driving, how far do they have to drive until they've seen everything or seen enough to know exactly what's happening between those two vehicles. Okay, so there's a little bit of a notation that we need to introduce. The first piece is we have this S of t is going to be the solution of time t. Basically, that says starting from some initial density, what's the density along the road at time t? And then gamma is going to be basically what each individual vehicle has seen, i.e. all of the densities. It's basically just driving and writing down the local density all along the road. And so it turns out that if there is a finite time at which you can reconstruct the traffic between the two PDE or between the two ODEs, then there's only then basically for some unknown initial data, if you reach a time where you can reconstruct it, there's a unique solution. And so I guess at a high level, the sketch of that proof is basically that if we assume the vehicles drive faster than the discontinuity, then basically any shock that existed at the start, the autonomous vehicle at some point will have seen as it's driving through. And so you just have to know sort of what the conditions are to be able to compute how long you're going to have to drive in order to have seen any potential interaction. And then going forward from that point, the automated vehicle sort of knows what the traffic conditions look like in front of it and is then able to determine how those new traffic conditions will interact with the traffic conditions that are behind it. So I want to sort of show a quick example because I think that might illustrate what's going on a little better. So it turns out that if you know the initial density, where the automated vehicle starts, you can relatively easily compute the time at which two automated vehicles, well, you need to know, sorry, the initial position of each automated vehicle and the initial density at the vehicle in front. You can quickly compute how far those vehicles, how long those vehicles have to drive until they've seen any potential sort of discontinuity in that PDE that could change the traffic state. And so you imagine some, pretty ugly initial density here. So we look at time here, position here. We have very low density. And then, so left to right, we have very low density, very high density, very low density, very high density. So if you look at the Riemann problem between high density, low density, that's going to create a shock that travels backwards. Then the Riemann problem between low density and high density, that's going to create a rarefaction fan. And then high density, low density, that's going to create another shock that in this case, because of the relative densities, is almost going to be stationary. And then we have these three automated vehicles. And so we want to know at what time has this automated vehicle basically seen everything so that it can know exactly what the state is behind it. And then at what time has this automated vehicle driven far enough so that it can know exactly what time, what the state is behind it. And so it turns out that using the result above, you can easily compute this time. And so right here, we're basically plotting based on what the automated vehicle has seen, what the automated vehicle thinks the state is behind it. And you see that basically once that time is reached, the actual state and the presumed state is guaranteed to be correct. Notice though that in this case, the automated vehicle had actually seen it, had the correct estimate earlier on, but it wasn't guaranteed to be correct. Whereas in this case, I think it took a little longer, and it really wasn't until that we reached that time that the automated vehicle actually had the correct guess based on the densities that it was seeing locally. Okay, so in summary, I covered quite a bit of ground here. So let me just quickly recap. So we started with human drivers are string unstable, and you can see this experimentally. And what this means is small perturbations are going to amplify until you get some sort of wave that travels through the traffic flow. Changing the dynamics of just a small number of vehicles in that traffic flow can substantially change the dynamics of the entire traffic flow. And that can be for the better or for the worse. So if you model, individual vehicles as ODEs, and then look at sort of fit those models to the behavior of adaptive cruise control vehicles, it turns out most commercially available adaptive cruise control vehicles, or at least all the ones I've seen, are string unstable. And then if you switch from thinking of automated vehicles as sort of changing the flow, controlling the flow, to just driving in the flow, but observing and seeing more, there's actually some really nice results that can be shown for coupled PDE ODE systems where you model the bulk traffic flow with that PDE and then the individual vehicles through that flow with the ODE. So I think we might have a little bit of time for questions. If not, thank you very much. I really appreciate the opportunity to come and talk here. Thank you.
Thank you, Rafi. We can do a virtual applause. Thanks again. We do have time for some questions. Anyone, please raise a hand and I can take you one at a time. Anyone with a question?
Looks like Alex, maybe.
Alex, go ahead.
So I have two questions. One of them is on the assumptions in the second half of your talk. Mm-hmm. You started by showing us how a small number of those autonomous vehicles can actually change the traffic flow. And in the second half, or rather towards the end, you said, but we're not going to change the flux in the PDE solution based on what those particles you're tracing with ODEs are doing. Yeah. There seems to be a contradiction. Doesn't it mean that you need to have them driving exactly as other humans would? Otherwise, they will be affecting the flow?
Yeah, you're absolutely right. And actually, the cool thing is that your question brings up a whole nother set of things that you can do that's even cooler. So yeah, you're absolutely right. The assumption, I mean, I think if you learned one thing from this talk, I think it's that changing the behavior of a small number of vehicles can change the properties, or does change the properties of the emergent flow, or the emergent properties of the traffic flow. And you're absolutely right that the assumption of the second part of the talk is we're going to ignore that. And so, I mean, I guess the easy answer is just pretend they drive exactly like humans. But I think the cooler answer is, well, yeah, and that allows you to control the solution of the PDE locally. And so you can imagine a strongly coupled PDE ODE, where you have not only does the solution of the PDE influence how the ODE can drive, but also the ODE locally changes the flux function somehow and therefore locally changes the solution to the PDE. And I think the example that you can think of here is, imagine traffic flow and you have a big bus or a truck that's driving in the traffic flow. And the bus is driving a little slower than the other traffic. And so you have, if you imagine a 3-lane road, now it's effectively gone down to 2 lanes with a moving bottleneck. And so locally where that bus is, you have a 2-lane road, and you might want to be able to model that bus separately. But in the case of automated vehicles, you can imagine that bus is, an autonomous vehicle, and you could actually control how that vehicle behaves in order to influence how the PDE evolves. So you're absolutely right, there's a contradiction there, but that contradiction can be exploited for even cooler math.
Thank you. I'll wait with my second question after others had a chance.
Anyone else? Well, Alex, I guess you can go again.
So you showed us that those autonomous vehicles are not really good at stabilizing the traffic flow, the commercially available ones.
Mm-hmm.
But stabilizing the traffic flow is, in some sense, a system level objective function. Yes, everybody wins, but if everybody else is doing it and I am not participating, maybe I can do even better.
You win even more, yeah.
And I'm the guy who paid the money for that premium type vehicle. Is it ethical to manufacture features in it which do not benefit me but benefit the society without telling me about this? So I guess my question is not on ethics. The question is on, are they not doing it simply because they never studied it? They're not generating string stability, or if they wanted to do it, would they actually sacrifice something for the owners of those cars?
Yeah, that's a really good question. I can tell you that it's definitely not the case that they haven't thought about string stability. I've talked to people at car companies, and I've talked to people in research who have sort of worked extensively with the car companies, and they, at least some of them, definitely have thought about this. And I mean, if you don't have to look far in the literature to find string stable adaptive cruise controllers that were published in the early 90s, right? This isn't something that's, from a control standpoint, it's actually really not that challenging of a problem. I think what happens is, I mean, so first of all, car companies want to sell cars that are safe. That's their first goal. And to be clear, these cars are all safe, right? These cars will not collide. And part of that is because they have things like emergency brake assist, that they will slam on the brakes if something goes seriously wrong. The second thing is they want cars that people are going to buy, right? And so that's sort of to your point of, if you're the one paying, you want the feature that's nice. And so they design these a lot for comfort. And so when they design for comfort, they want to design it so that people like to use it. The question, there's something else though, and I'm not entirely certain where it's coming from, but even the cars that I've been told were implemented to be string stable still way overreact. And I think it has something to do with it's possible that their model of the system isn't 100% accurate. And therefore, when they implement a string stable controller on a slightly different dynamics than the vehicle dynamics are much more complicated than, I mean, to properly model vehicle dynamics, you need a 1,000-dimensional space, right? And so I think I'm not sure if that's what it is or if there's additional lags that they're not accounting for. But the fact is that from a traffic flow standpoint, they are string unstable. And it might also be that they, that they say at the end of the day, look, our number one priority is safety. Our number two, in theory, string stability and safety should come hand in hand. Number two priority is comfort. So the number three priority of string stability doesn't really sell more cars, and so is not critical to address. I don't know what the answer is.
So just a quick follow-up on this one. So how would it jeopardize the comfort if I were to try for string stability? How would it become less comfortable?
You'd think they would go hand in hand as well, right? There's no obvious reason why a string unstable vehicle would be more comfortable than a string stable vehicle, but it could be that a string unstable vehicle has to, for example, a string stable vehicle has to make more adjustments, which could be perceived as more jerky or something. It's possible that something like that, but it's not obvious. I mean, in theory, they should go hand in hand as well.
Just
Thanks.
follow-up related to that, could it be also that the string stable vehicle has to keep longer headways and the driver might be annoyed if it...
Yes, Samita, that's a really good point, is that the easy way to make anything string stable, or not anything, but pretty much anything string stable, is to drive further away. If you've got half a mile in front of you, it really doesn't matter how badly you behave. It's not going to affect the next vehicle, right? The downside here is sort of twofold. From a throughput perspective, I mean, if you're driving on an empty road and there's not a lot of demand, that's fine. But from a throughput perspective, and that's really a big part of what I care about, having larger headways, if you space everyone out twice as far, you can fit half as many vehicles on the road, you've cut your throughput in half. And so the other thing is people don't like, so from the rider comfort perspective, one thing that people don't like, and the biggest complaint when I say, oh, I study adaptive cruise controls, the biggest complaint people give is the thing leaves too much space. People love to drive really close to the person in front of them. And the adaptive cruise controller doesn't like to do that. And so if you were to increase that spacing even more, you would basically, people would feel like there's other cars cutting in front of them. And so then that kind of, nobody would actually end up using it, I think. So really, Alex, they're very good questions. Like those are definitely spot on in terms of what's going on here.
I think maybe we have time for one more question. Max, though. Oh, sorry, I didn't see your hand. Please go ahead, Maximum.
Okay, so my general question is like, so when you were talking about string instability, you were talking about it as like a property of a single car. Like I have a bunch of cars, but I decide whether or not I have the whole string being unstable by like, if I have a bunch of the same car, how does it go? How do you translate that to like all of the cars? If all of the cars are string unstable but differently, is there anything funny that you can see there, or is it that simple?
So if I understand your question correctly, you're saying I'm talking about string stability both in terms of a property of the car and in a property of the flow.
Yeah.
Which is it? Yeah.
And like how do you translate like a mix of cars?
Yeah. Okay. So that's a really good question. Because so to be clear, string stability is a property of the flow, right? We need that disturbance to propagate through that flow. What I'm saying is if our entire flow is homogeneous, then we can basically look at the individual vehicle and see how that's going to behave. It turns out now you've caught that I've basically skipped a big step here and said, okay, fine, but we need them all to be homogeneous, but we're going to look at one individual vehicle, right? And so it turns out that you can also look at the mixed traffic flow. The math is just a little uglier, but you have very similar results that hold. And vehicles that are string unstable individually, if you mix them with string stable vehicles, depending on how much you mix them, you can either get string stable or string unstable flow. And so it just is a matter of, it's just slightly uglier math, but nothing that's like actually more challenging. It's just more, right? But basically there's a way to look at the composite property of the entire flow. If you look at both, if you look at a mix of both string stable and string unstable, or differently stable and unstable vehicles, right? You can mix some highly oscillatory vehicles with some not so oscillatory vehicles and see what that composite flow is going to look like. And basically, so I mean, I guess to answer your question specifically, the analysis is the same. You're going to look at the analysis is pretty much the same, only that you have to look at sort of platoons of vehicles. The other thing you can do is if you have a platoon of vehicles, you can look at like the H infinity norm of the state and look at how that evolves, and that's going to tell you the same thing. but computationally gets challenging for larger platoons.
Thank you.
Okay, so I think Erica sent a link to GatherTown. So I think maybe we will, if you have any more questions, we can move the discussion to GatherTown. And thank you, Rafi, again, and we'll see everyone there.
Thank you. I'll see you over in GatherTown.